So that's the first big observation that we want to make here. Contrary to the curvature kappa, which we have the formula from before, that kappa, right, the curvature kappa is just the second derivative. This formula right here. Kappa is the second derivative of position with respect to arc length along the curve. Right, so contrary to kappa, the torsion actually depends on the third derivative of position with respect to arc length. But this is a very nice equation, and this essentially gives us a process for calculating the torsion along any curve, provided that the curve is parameterized with respect to arc length. Now we could re-express this in terms of a general parameterization. So this is, remember, all of these primes here denote the derivative with respect to arc length s. So if we need to say, do this with respect to a parameter t, so reparameterize, we're going to have to do that suitably. R prime dr ds is the same thing as dr dt divided by ds dt, or dr dt over v, magnitude of the velocity vector. So each one of these derivatives would also have to be changed according to this rule right here. So you have to be very, very careful if you're going to try and do this with respect to a parameterized curve with respect to a different parameter. But it'd be a good exercise to go through and do yourself and to kind of see and experiment with. And the last thing that I want to talk about in the lecture today is how to apply the Frenet-Serra formulas to general motion of a solid body. So suppose the following. We'll consider a solid body. And the trihedron or the Frenet frame that is frozen into the body. At some point Q in the body. And we'll assume that this frozen frame is moving along some curves. The body is actually in motion along some curve in 3D. So we'll start by drawing this. Trajectory. And then we'll say we'll visualize this at some point. Q. So this is our solid right here. And you have this point Q inside of the body that's frozen, where it's following this curve C. And we have the definition of the normal vector, the tangent vector, and the binormal vector. That, remember, is fixed inside this body on this point Q. And now we will consider another point on the body. We'll call it point P on the body. That's a different point on the body. Maybe let's make this a little bit bigger too, just to sort of illustrate this point. So the first thing to notice is that from the origin, call it O, over here we have a position vector out to P. Just like we have a position vector out to Q. And we also have a position vector from Q to P. So what we want to consider is the motion of this body and the relative motion of this body, and how we can kind of describe that motion and understand that motion. So first off, we will describe this position vector, the position vector of point P, as capital R of t. We'll describe the position vector out to point Q as lowercase r of t. Lowercase r of t is connected to this tangent, normal, and binormal frame, the Frenet frame, through the formulas that we talked about before. And lastly, we'll call rho of t the distance between Q and P, the distance out to P. So one way of expressing R of t is that R of t is equal to the position of point Q plus rho of t and the first thing that we want to notice is that we can make the following simplification. Because t hat, n hat, and b hat are fixed with respect to the body, and so they're not changing their orientation with respect to the body. This vector rho of t has a very nice expression. we can express rho of t as a constant, rho 1, times the tangent vector as a function of t, plus another constant, rho 2, times the normal vector, unit normal vector, as a function of t, plus the constant rho 3 times the binormal vector as a function of t. And let's just make sure that we underline our vectors, because that's the notation that we're trying to stick with here. So what that means then is that this vector r of t, capital R of t, is equal to lowercase r of t plus this summation right here. Rho 1 t of t plus rho 2 n of t plus rho 3 b of 3. And it's really important to point out here that rho 1, rho 2, and rho 3 do not depend on time, or on the parameter t. Because P and Q are frozen into the body. So even if the body is rotating, as it moves along the curve, these 2 points are fixed relative to one another. So what's really giving us our this constancy is that they're fixed relative to one another. So in the Frenet frame, the expansion rho 1 times t plus rho 2 times n plus rho 3 times b is always going to be the same. T, n, and b are going to be changing with respect to time, but that's normal. And this is going to give us a big simplification. Because if we want to say figure out the rate of change of the point P with respect to the point Q, or dr dt, this is going to be equal to, this is the velocity vector of the point P. This is equal to the rate of change of r with respect to time, or the parameter t, which is the same thing as the velocity of the vector of the point Q, plus rho 1 times the rate of change of t hat with respect to t, plus rho 2 times the rate of change of n hat with respect to t, plus rho 3 times the rate of change of b hat with respect to t. Or the velocity of the point P is equal to the velocity of the point Q plus this entire sum right here. And recall that we have our Frenet-Serra formulas that we can use, but those Frenet-Serra formulas are all relative to the derivative with respect to arc length, not with respect to some parameter time or any other parameter. So we have to be a little bit clever here. Recall that the derivative of anything with respect to time is going to be the derivative of f's with respect to time times the derivative of u with respect to s. And this is how we have to the chain rule, and the chain rule again, this is how we have to translate our derivatives. So we have here the equation that the velocity of the point P is equal to the velocity of the point Q plus rho 1 times, remember here that ds dt is just the velocity of the point Q. In magnitude. This is going to be the magnitude of the velocity of the point Q. This is ds dt times dt hat ds plus rho 2 times the velocity of the point Q, because this is ds dt, times dt hat ds, or dn hat ds, plus rho 3 times the velocity of the point Q in magnitude, times dp hat ds. Which all simplifies a little bit if we rewrite this as the absolute value of, or the magnitude of the velocity of the point Q times rho 1 times dt hat ds plus rho 2 times dn hat ds plus rho 3 times dp hat ds. And now that we have all of these unit tangent vectors from the Frenet frame, and the derivatives of them in terms of the arc length s, we can go through and apply our Frenet-Serra formulas to get a very nice expression. This ends up being a little bit long at first, but it will simplify greatly. The first Frenet-Serra formula gives us that this is rho 1 times kappa times n. The second Frenet-Serra formula gives us that this dn hat ds is negative kappa t hat negative torsion tau times b hat, and the third Frenet-Serra formula gives us that db hat ds is just equal to tau times n hat. I'll put this in parenthesis here. But we can go through and directly simplify this equation to look a little bit nicer. And then we'll see that it simplifies even greater. So this expression simplifies to negative rho 2 kappa t hat plus rho 1 kappa plus rho 3 tau n hat minus rho 2 tau b hat. And it's a good thing to check this out, take the following expression out, and think about what this is actually equal to. And sure enough, after some thinking, you'll end up seeing that this is equal to the following. It's exactly equal to the magnitude of VQ multiplied by the vector negative tau t hat cross product with kappa b hat, and this is then the cross product with the vector rho. So this expression right here is the same thing as this expression right here. And this is something that you're definitely going to want to go through and check for yourself. It's relatively straightforward to go through and do so, but this is what's going to end up popping out when you go through and do this cross product. This is a very, very special vector. This vector is a vector that we call the vector omega. It has a very special name. It's called the Darboux vector of the frame. It's a vector that it depends on both the torsion and the curvature. However, if we rewrite this as using this Darboux vector, we see that the motion of the frame, the formula for the motion of the frame, specifically for the velocity of the frame, the velocity of any point P on this body, is uniquely determined and directly determined by the velocity of the point Q on the curve and of this the cross product of the Darboux vector, which is changing with respect to time, with a constant vector rho. And the main result here is known in kinematics of a solid body, with this vector omega called the angular velocity, the perceived internal angular velocity. So this Darboux vector has a fancy name, but essentially this is known in kinematics and physics as the perceived angular velocity of the solid body. So omega here is, you can think of it like the angular velocity vector, or the perceived internal angular velocity vector at that point inside the body. So what's neat here is that our analysis has made it possible to specify this omega as the Darboux vector associated with the trajectory c, traced by the point Q of the body, and it has essentially showed us how to deal with rotational motion in kinematics. This is the correct way of dealing with rotational motion in kinematics. If you have a solid body with fixed points in the body respective to each one of one another, this decomposition works out very nicely. And it's a great example of how to apply the Fresnel-Seurat formulas and how to use the Fresnel-Seurat formulas in general. But thank you very much for turning into lecture today. I hope you had a great day and learned something new.